All right, here we are with the first section in Chapter 7, Writing and Balancing Chemical Equations. As always, the learning objectives are provided here for you, so please pause the video and take a moment to write those down. Okay, so what we see first here is a picture of what happens in chemical reactions. Okay, so some important terms and things we need to become familiar with if we are not already comfortable with them. So first thing is we have the yields arrow in the middle here, separating the reactants from the products. So reactants on the left, products on the right, separated here by this arrow. This arrow means yields. Okay. Additionally, you can have plus signs on each side of the reaction. Those plus signs are used to separate elements or compound substances from one another. So you can see in this case we have two substances on the left and two substances on the right. The plus signs are used to separate those. The other thing you'll notice here is we have coefficients. So they're highlighted where they're located here, the 2 in front of the O2, and here again, the 2 in front of the H2O. So law of conservation of matter tells us that, matter is neither created nor destroyed. So when I have a chemical reaction, what happens is atoms are rearranged. So bonds are broken, new bonds are formed. But whatever I have to start in my reactants, I must have the same atoms and amounts of those atoms when I'm done in my products. So our task in this unit is going to be balancing chemical equations. So what I can do to balance my equations, the only thing I can do is add coefficients. Okay, so we know this by now. We've done formula writing for ionic and covalent compounds and acids. We understand that this CH4 is a specific molecule with 1 carbon and 4 hydrogens. I cannot change that 4 because then I've changed the molecule completely. We understand that this oxygen here, even though it's just an element, just an atom of oxygen, it has a subscript 2 because it's a diatomic. We remember our Hofbrinkel, really important that we remember those Hofbrinkel elements. So when they're by themselves in a reaction, they will have a subscript 2 like you see there with the oxygen. Again, over here, this is, as we know, carbon dioxide. Again, if I changed the number of carbons and changed the subscript from a 1 there, or the number of oxygens from a 2, I would no longer have carbon dioxide. So I cannot at any point change any of those subscripts. Those are the specific molecules or compounds, and I cannot do anything to those to balance my equations. What I can do is add in coefficients. One of the things that we need to understand there is when I do that, so if I take a look at this 2, for example, in front of the H2O, that now affects both the hydrogen and the oxygen. Okay, so right now over here, I have 4 hydrogens and I have 2 oxygens because of that subscript 2 that's been placed in front of the H2O there. I'm sorry, the coefficient 2 that's been placed in front of the H2O. When I have a subscript next to an atom, it just affects that atom that's next to. So right here, I have 2 oxygens. Okay? So our goal is going to be to make sure when I'm done my reaction that whatever atoms I have on the left, I have the same atoms on the right in the same amount, in the same number. So if I took a quick look here, I would see on the left side, and it's by side, it's not by individual compound. So on the left side, I have 1 carbon, I have 4 hydrogens, and I have 4 oxygens. Okay? If I took a look over here on my right side, I would see I'd have 1 carbon, I'd have 2 oxygens here, plus 2 more here, so a total of 4 oxygens, and then my 4 hydrogens. So you can see on both sides of my yields arrow, I have the same amount of each atom. That's going to be our goal in this unit, so we'll take a look at some practices and some different little techniques here in a second. Okay, so if you've ever balanced equations before, you may have, there's a technique that some people do where they kind of make a little table and say, reactants, products, okay, and they determine actually what I have. So in this first reaction, I have 1 and 2 iodine. And over here in the products, I have 1 and 3 iodine. And they look at what they have and they balance those numbers out, and then they go back in and do it that way. You may have seen this way before, you may have been taught this way. I actually prefer just to jump in and start working my way back and forth and balancing that way. So for example, I would look at this first reaction and think to myself, okay, what jumps out at me there is not being balanced. Well, the antimony SB is the same on both sides, but clearly I have a different number of iodines, of I. So the way to balance those would be to put a 3 here and a 2 there, giving me 6 on both sides. Now, here's the point of when I put my coefficients into balance, I'm often going to knock something else out of balance. So I said at the beginning my SB was balanced. Okay, but now I've put this 2 here. So now I've given myself 2 SBs on the right. So that means I have to bounce back over here and put 2 on the left there. Okay, and so you can see that balanced it out. I think it's a little quicker, maybe not as efficient, because sometimes it doesn't work and I have to kind of erase and start all over, which you'll see here in a second. But again, I'd take a look at this next one, and the iron immediately jumps out at me. I have 3 on the right and 1 on the left, so I'm gonna put a 3 there to balance my iron. Okay, I have 4 oxygens on the right, 2 on the left. So if I put a 2 there, I balance my oxygens, and I'm done there. This last one, any type of, this is a combustion reaction. Typically, combustion reactions can get pretty complicated in balancing. You'll see what I'm talking about here in a second. So this also illustrates another point, that a little trick that I use is that I'm not going to worry about balancing the oxygens initially, because oxygen shows up in 2 different compounds on the right. So I'm just going to wait and balance everything else and kind of see what that does to my oxygens. So in that case, let's start with the carbons. I have 8 carbons on the left. Carbon is right here on the carbon dioxide, so I'm going to put an 8 there to balance my carbon. I have 18 hydrogens. So in H2O, in order to get 18 hydrogens, I need to put a 9 there. Okay, so now let me think about my oxygens. So currently right here, I have 9 oxygens here, and I have 16 oxygens here, okay, for a total of 25 oxygens. Okay, but because of this diatomic here, I can't get 25, all right? I need to have an even number here. So you see that this is where we have a little bit of an issue. Now, you will come across some situations where they'll put fractions in front here, but we want to, at this point, focus on balancing with the lowest whole number ratios here. So what that means here is what I have to do is I have to start over. All right, so and the first thing I'm going to do when I start over now is put a 2 here. Okay, so now that means I have 16 carbons. Okay, that means I have 36 hydrogens, putting 18 there. Okay, and so now let's see what that does for me. That means I have 32 oxygens here and 18 more here for a total of 50 oxygens. So now I can get that, and I can put 25 times 2 gives me 50 there. Okay, you can see here how large these coefficients are. Okay, as I mentioned at the beginning, Combustion reactions like this can get a little complicated. Nothing wrong with that. That's the simplest whole number ratio. I can't reduce those down because of that odd number, that 25 there in the front. All right, the other thing we need to do at this point in time is we need to be able to put all of our expertise in naming and formula writing to work to be able to handle what's known as a word equation. So I have a word equation here in front of you. When dissolved, beryllium chloride, so beryllium chloride is ionic because of a metal, so beryllium is Be2 plus, chlorine is Cl minus. So I'm going to have BeCl2 reacts with, that means plus, dissolved silver nitrate. So again, let me think about what that is. Ag plus NO3 minus. Okay, cross the charges, I get AgNO3. In water, aqueous beryllium nitrate and silver chloride are made. So that's my yield arrow. And now I'm going to make beryllium nitrate. And you can see I already have these ions here. There's beryllium, there's nitrate. So cross those charges, I'm going to get BeNO3 and there's that plus sign, silver chloride. Again, I have the two ions already written there. And cross the charges, I get AgCl. Now I need to balance this. Okay, and so once again, the thing that jumps out at me as not being balanced right off the bat is that nitrate ion. Since the nitrate stays intact on both sides, I can balance it as one thing. So I have two nitrates on the right, so I need to come over here to the reactants and put a 2. Again, that's probably going to do something to my silver. Let me check. So I bounce back over to the right. Yes, I now have 2 silvers on the left, only 1 on the right. So if I put a 2 there, I balance my silver. That's going to affect my chlorine, so let me bounce over here, and I see I already had 2 chlorines there, so that should now be balanced. So this is a word equation. We need to be able to take a full written out equation like this in word form and put it in formula form and then balance it. The other piece of the puzzle we want to add here are the physical states of the reactants and products. So you'll see that gas, liquid, solid, or aqueous. In that last example, when I said were dissolved, that's an aqueous solution, dissolved in water. Okay, so that's the AQ. So you can see here we need to get to the point of starting to also identify the states that our reactants and products are in. So you can see here solid, liquid, aqueous, and gas. Okay. All right, so now where this is headed is this equation that I just did in this last word equation. That is a molecular equation. Okay, so all in compound form and balanced, that's a molecular equation. There's actually what we're going to talk about here are molecular equations, complete ionic equations, and net ionic equations. This is going to lead into 7.2, so I really just need this at this point in time to be a little bit of an intro. We'll focus in our pre-class quiz and homework on balancing and word equations at this point, and then we'll get into net ionic equations when we talk about types of reactions in 7.2. But just as a little introduction, here's where we're headed. Okay, we're going to just be given this now. Aqueous calcium chloride reacts with aqueous silver nitrate. So, okay, so calcium chloride is Ca2 plus and Cl minus. I always just write these ions down there. I'm going to need them. It helps me. I jot them down real quick, and then they're right there for me to see, and I don't make any mistakes with the crisscross method. Silver nitrate would be Ag plus and NO3 minus. Okay. Cross the charges. I get CaCl2. Aqueous means AQ. Plus reacts with means plus. Silver nitrate. Again, aqueous means AQ. Okay, so now this is a type of reaction. It's a double replacement or double displacement reaction, right? So atoms can either be created or destroyed. One of the things I said happens is they are rearranged. Bonds are broken and new bonds are formed. So if I wanted something new, what would I'd only have one option for this positive, calcium cation to react with in order to give me something new. It would have to react with this nitrate anion here. And so I would get Ca cross the charges, NO3, 2. Now we're also going to have to think about and determine what state that's in. I'll get to that in a second. Okay, then I'm left with a silver cation and a chloride anion. So I'm going to cross those charges. I'm going to get AgCl, and again, I'm going to stop. I have to think about what states those are in here in a second. So there are a set of solubility rules that you'll be responsible for, and you'll see those in section 7.2. If you went through those rules, you would find that calcium nitrate is aqueous and silver chloride is insoluble, and so I would mean that would mean it would form a solid. So you have to remember what's happening here. I don't have calcium chloride. What I have are calcium ions and chlorine ions floating around in solution. That's what aqueous means, dissolved in water. And then I have silver ions and nitrate ions floating around in water here too. Real quick, I forgot to do something to finish this molecular equation. I'll just call it Me for now. I got to balance it, so don't forget to do that. Again, I have 2 nitrates on the right. There's 2 there. 2 to balance my silver. Okay, so that should be balanced now. Okay, so you have these ions floating around in solution. That's what aqueous means. And if there are 2 ions that would form a solid that are insoluble, they would precipitate out and a solid would form. And that's what's happening here. Solid silver chloride would form because calcium chloride brought chlorine ions, the chloride anion, and the silver nitrate brought the silver cation, and those 2 ions are in the same solution together. They would attract, form a bond, and precipitate out in solution and get a solid. And that's important to us because it indicates that, yes, a reaction here is going to occur. Once that happens, I want to be able to understand or pinpoint, focus in on why this reaction is actually going to be a reaction. Something's actually going to happen. So we're going to talk about the molecular equation, and then we're going to talk about the complete ionic equation. All right, complete ionic equation. The complete ionic equation is literally everything written out as its ions except the solid. Okay, so to do that, I would say calcium 2 plus aqueous plus 2 Cl minuses aqueous plus 2 silver ions aqueous plus 2 nitrate ions aqueous yields a calcium ion and 2 nitrate ions, and then that solid silver chloride. So again, the solid does not get broken up. It stays intact as a solid. It's precipitated out of solution. So that is my complete ionic equation. The next thing here is the net ionic equation. Okay, so in order to go from the complete ionic equation to the net ionic equation, you cancel out or cross out the spectator ions. Spectator ions. Okay, and those are exactly what if you think about spectators at a sporting event, they're just watching, they're not participating in the game. Same thing's happening here. Your spectator ions are just watching, they're not participating. So it's the ions that show up on both sides of the arrow. So you can see here that I have a calcium ion on the left and the right, so I'm going to cancel those out. That's a spectator ion. All right, the two nitrate ions on the left and on the right get canceled out. So my spectator ions here are the calcium Ca2 plus and the 2NO3 minus ions. That then leaves me with what has not been canceled out, which is the net ionic equation. So the final net ionic equation would look like this. Okay, and so technically, because there's a 2 in front of everything there, I could also write this without the 2's because a balanced equation is the lowest ratio, and so those could all cancel down, and I could technically write this as this net ionic equation. So as I said, as we wrap up 7.1 here, we'll let that last piece of this just be an introduction. We'll focus here moving forward with your pre-class quiz and our classwork next time in the homework on balancing and writing word equations into formula form.